Hello, I'm Aaron Lee from Carnegie Mellon, and it's my pleasure to present you the joint work with Emma, Sujis, and Alex. Today, I'm going to talk about some fundamental techniques to make topic models run faster. So obviously, all of you here are already experts of the subject, so let me just quickly go through the basics and the current state of the art, the shortcomings, and then I'll show you how our alias method speed things up. It doesn't only work for LDA, but also can be generalized to work with more sophisticated topic models. For example, Pitman-Ure topic models and hierarchical dirichlet process. So, okay, let's get started. This is a good old LDA model that everyone loves. And this is a standard application of LDA. It's used across all fields of data science to analyze billions of documents, images, videos, and user activities and everything. And this is a standard sampling equation for collapse skip sampler. So let me introduce the notations I use. T is a topic, D is a document, I is the document index, and J is a word index. Everything else is standard. For example, NTD is a document topic count, and NTW is a topic word count. The standard way to speed up collapse skip sampler is to look at some sparsities of each term. As for example, the NTD part have only a few non-zero entries for OT. Because documents are short and each token in the document contributes no more than one topic. So similarly, NTW is also sparse if the average word frequency is low, which is generally true for small collections. Sparse LDA is created using this principle. The sparse terms are expanded as a multiplier for each term, and it's very effective for small collections. And you can see that each term they are all sparse. But it's not true for large collections. In large collections, the word frequency is a lot higher, and the NTW variable becomes dense. The sampling performance falls back to naive algorithm in the worst case. The same issues also appear in other topic models, and that is Poisson-Dirichlet process. And the other is hierarchical Dirichlet process. There are just two examples. So their sample equations are very complex, and they don't even decompose to sparse terms, even for small collections. So we do something different. In addition to sparse decomposition, like in the state of the arts, and there is an often neglected property in topic models, that is, the word emission model is slow changing, unlike the topic distribution for each document. So I'll use LDA as an example, show you how we use this property to approximate the slow changing part, it's on the right, and reduce the sampling complexity to only one sparse term. Namely, I'm talking about the part on the left, and fundamentally reduce the running time for all topic models. The first ingredient is Metropolis Hastings sampler is very simple in every statistic book. First of all, we decompose the sampling equation in a different way to make the dense part match exactly the slow changing part in the model. So as I discussed before, the sparse part can be sampled very quickly. So instead of sampling from the dense part directly and recompute the probability for each outcome every time, we can just draw samples from an approximate static distribution. And a static distribution has a constant normalizer apparently. So therefore, at first, we reduce the normalization complexity from order k down to order KD, where k is the number of topics and KD is the number of non-zero topic counts in the current document. D. So to make things clear, we can rewrite the equation in a simple way. A sparse term depending on the document and the current word, and a dense term depending only on the current word. Having only the approximate distribution Q at our disposal, with Metropolis Hastings, we are still able to sample from the true distribution P if we follow this procedure. So assume we have an old sample called X prime, and we draw a sample X from Q, the proposal distribution, and then we compute the acceptance probability of X prime to X with the equation in the middle. And this can be done very quickly because we only need to evaluate two ratios. It's constant time. So therefore, if there's a way to sample quickly from the dense part, we would be able to reduce the sampling complexity down to order KD if the quantity doesn't really change with respect to the size of the corpus and in practice very small. So in addition to that, under the generalized form on the top, our method could work on many topic models as long as we are able to simply rewrite the model as a summation of these two terms. So to quickly sample from the dense distribution, as I mentioned before, we need a second ingredient. It's called alias sampling. Walker's alias method is developed by Alistair Walker in 1977. It works this way. Given a discrete distribution, it compiles the distribution. It compiles the distribution into a static table, and afterwards, drawing the sample from the static table only takes constant time, instead of some time linear to the number of outcomes. So let me briefly go through the algorithm. So at first, we have a distribution where each outcome has different proportions. We go through all the outcomes and find the average value of the proportions. And then for each outcome with proportions less than the average, we take part of the proportion of another outcome and to make it reach the average. As we take from another outcome, we keep track of the origin. And we keep doing this until we get all outcomes reach the average proportion. So in the end, all outcomes reach exactly the average proportion. That's why it's called average. Obviously, at this point, each outcome is composed by no more than two parts, two components. So its original proportion and part of the proportion from another outcome. So to draw samples from this static table, we only need to generate two random numbers. The first random number decides which column we are going to look at, and the second one decides which component we are going to take. So back to the original sampling equation. The first term is sparse and can be sampled in order KD. And the second term is dense but static, if we use the alias method, it's a perfect way to compute a static approximation for the dense term and generate samples from it. The build process of the alias tables can take place in a background thread for every word W repeatedly in parallel with the main sampler. So this ensures the sampling complexity of our alias sampler is no more than order KD. And the approximation distribution is close enough to the real distribution so that the acceptance probability in the Metropolis-Hastings sampling is high enough. So let me show you some results of LDA, PDP, and HTTP in terms of quality and speed. And all the results are generated using a single-thread C++ implementation on a laptop with 1.73 gigahertz of CPU. The first result is between sparse LDA and alias LDA. We vary the number of topics. We compute the running time against we compare the running time against the number of iterations with different number of topics. The solid lines are running time of sparse LDA, and the dotted lines are for alias LDA. And when the number of topics 256, they are in the bottom. They are about the same. However, if the number of topics increases, the alias LDA scales a lot better, and it's a lot faster than sparse LDA. And in the end, it's 100% faster. And it concerns with our theory, the KD changes slower than with respect to K, as opposed to KW. Similarly, alias LDA scales a lot better than sparse LDA when we vary the amount of data. So for sophisticated topic models like HTTP, PDP, the time complexity is directly reduced from order K down to order KD, and that speed up is huge. So, by the way, we employed block table indicator sampling developed by Ray Buntine, the previous speaker, and he is also my bachelor honors thesis supervisor back in Australia, and his students Chang Yu Chen and Lan Du. And all this speed up comes without any sacrifice in convergence time or quality. The alias method and the original method converge to the same exact perplexity in the end. And you can also see it in the middle as well. And so to summarize, we showed 4 things. We showed a new way of sparse decomposition of general topic models. We also showed a new sampling method using Metropolis-Hastings sampler and Walker's alias method. And we showed a significant speed up over the previous state of the art, and a sampler that's able to process more than 1 million tokens per second with only a single thread on a laptop. It's far more than what's capable of the previous state of the art, for example, Yahoo LDA, which processes about 250,000 tokens per second with 8 cores. Before I finish, I want to show you some of our extended results. At Google, the implementation of LDA extended into a parallel and distributed environment with thousands of machines. And it turns out alias LDA on the same scale is not only faster, but also converge to better perplexity compared to sparse LDA. And the differences in speed is in orders of magnitude. Well, that's it.